Working well now?
So, my name is Dean Hanson, come from the Danish Technical University, and I should like to introduce the first speaker of today. That's Roxoliana Zatserkovna, who will talk about augmented reality-based nutritional label recognition and visualization for food packaging. The floor is yours, Roxoliana.
Hello again, everyone. So my name is Zatserkovnyi, and I will be the one presenting today. So let me just turn on the screen share, and I will go through the talk, which is actually our second one today. So, okay, if everyone can see the Chrome window, which can everyone see the slideshow at the moment?
Yeah, we can. We see presentation.
Okay, perfect. So our second talk today is going to be on the subject of AR-based nutrition label recognition and visualization for food packaging. And the summary of our talk is we'll first start with an explanation of nutrition labels and why they are hard to interpret by users or consumers rather. And then some related work like developing more simplified formats for labels, digital overlays, AR applications, and so on. And then our methodology, which is to create an OCR pipeline for recognizing text on printed labels, and then visualizing them using AR. And we will show some results of recognition on real Ukrainian packaging and talk a bit about our next steps as well. So, the main idea behind our talk is that nutrition labels are meant to guide healthy choices by consumers. So they're not only a legal requirement in many jurisdictions, they actually give consumers details on nutrient content and support informed choices on food which they consume. But in practice, these labels are often formatted in a way which makes them difficult to interpret. Fonts used in nutrition labels are small and layouts are unfortunately crowded. Even if the information is easily visible, many people do not know how to interpret it. So, for example, a protein value of 8 grams or a sodium content of 500 milligrams may be read without any sense of if it's high, low, or somewhere in between. And these gaps in comprehension are actually a serious concern because they can influence purchasing behavior and mainly prevent consumers from having a healthy and balanced diet. So one particular study which we cite in our article found that actually 41% could not calculate how much of a percentage a single food is in their daily caloric intake. 42% could not estimate carbohydrate content, even though it's a number on the label directly. 24% could not even determine the calorie content. And on the other hand, so this kind of goes both ways, higher label comprehension was linked to healthier dietary patterns like lower soda intake. And the main idea behind our research and our article is to utilize augmented reality in order to display clear information directly on the package. Because a nutrition label can be easily processed with using a simple phone camera and turn it to a much more comprehensive format with a short explanation, for example, of what each component means, so what each nutritional component actually stands for. So let's now move on to our next section. So prior attempts to improve comprehension have moved in different sorts of directions, so to speak. One of them is to modify the format of the labels themselves, like create front-of-pack labels. And the general idea is that if labels are placed at the front of the package, they are forced to be simplified in a way and summarized, so they are designed to reduce the cognitive load of a person, so basically they don't have to decipher what the small text means on the back of the package. But a shift in perception, unfortunately, is very small, so one study has found that it only results in like 2.5% increase in healthy baskets. Now, there are other approaches like digital solutions, so browser-based overlays and mobile labels. And the idea is that many people today actually don't go to a physical shop. They do this shopping, for example, in a service which lets you deliver food from supermarkets. It was particularly common during like COVID quarantine times, but it's stuck around due to its convenience, of course. and has been gaining traction in recent years. So AI is sort of an extension of that idea because it can apply when a person goes physically into a supermarket. So a control study for nutritional education specifically found that an app which guides users to the correct panel on real packages and explains carbohydrate information was well-liked for participants and increased scores in terms of the selection of healthier brackets. So now on the technical side, making explanations work reliably on real packaging is not so much an AI problem, because like the task of placing objects in physical space has been solved well. It's mostly an OCR problem, because we need to read this small stylus text under very imperfect conditions. So classic OCR such as tesseract is a common baseline for this printed text, but for text in the wild, more modern solutions may be necessary. So these are typically convolutional neural networks, so they have to do with detectors like EAST and recognizes based on convolutional neural networks, so CRNNs. They're good foundations, and nowadays they are lightweight enough and phones are powerful enough that they are practical to run on mobile class hardware. Now, one more thing is that in retail, perceptions of packaging quality are actually a significant factor if whether a consumer decides to make a purchase. So visual work can act as hints that product is contaminated, even if there's no objective justification for this. And something which we actually cover in our other talk. And this means that the visual presentation choices in AI overlays should be ideally clear, legible, and actually more legible than what is presented on common packages. So our methodology actually has two parts, so to speak. So it's first an OCR pipeline, and then an AI pipeline which uses its results. So the idea behind our OCR pipeline is to begin with image acquisition and normalization, select the right candidates where text can be located, then recognize it using the tesseract library, so this one which I have mentioned before, with English and Ukrainian models, because we tested this out on Ukrainian packages primarily. We then parse the text, normalize into standard units, which is something I'll cover in the next slides. And then the output of our solution is further standardized JSONs showing the contents of energy, fat, sugar, protein, sodium, and several other elements which are standard for this type of nutritional labels. So the workflow of our pipeline is actually as follows. First, we convert an image to grayscale because we only need to work with text, normalize it in the CIE lab color space, and then we run through several steps. So it is, first of all, a noise reduction, so using adaptive thresholding. Then it's region detection. We use connected point analysis to find rectangular nutrition labels. And we assume that nothing particularly fancy was done in packages. So nutrition labels are rectangular, they kind of separated from the rest of the packages design, and they contain visible text in it. So for each of these candidate regions, we apply the OCR functions and extract nutrient entries. And this combines regular expressions like, detecting phrases like calories or the Ukrainian equivalents which are kal, kakao, and similar was to this. And the idea is to extract these items and then actually standardize them with a normalization functions. So we convert units to standard ones, for example, for calories, it's kilocalories. Then for sodium, we typically use milligrams. For other items, it's likely grams. Or you can also do conversions to determine whether it's like the total number of calories or calories per 100 grams, if those numbers are both specified, typically they are. And what we do is actually we normalize them to per 100 gram values either way. And the next step is actually visualization, so to create an AI overlay with nutrient explanations, simply showcasing the information which we have extracted so far. So some of our results are shown here. So you can see that this is a real-world image of a Ukrainian package, not in the most perfect condition, but our pipeline has managed to sort of zero in on these rectangular sections, which is actually the calorie section, and extracts the following info. So I believe if you compare this image to the results, it's not quite obvious in Zoom. Basically, there's a small error in one of the items. I believe this one is shown as 37 grams instead of 57. The others are essentially correct. And so our system works with both packages like this. And then this is kind of the back of a candy. So you can see that the rectangular region is still present, and this is detected in our system. If many rectangular regions exist, we simply use regex to find sort of common patterns like calories, grams, milligrams, and this way distinguish like for example, the table of contents in different languages from the caloric information which is in this rectangular section. And this also works for this, I'd say, easier sort of example. And in here, it's located in this area. And in this way, we sort of discard the total values and take the values by 100 grams. So the next steps in our work are actually automated explanations. So for now, we basically show an AI equivalent of this table in augmented reality, but the idea in the future is to assign it some meaning. So for example, we can warn the user if the sugar in a product or in the basket exceeds some daily limit, highlight beneficial nutrients, and integration with different health apps. This is like in the far future, but we have built-in solutions like Google Fit, for example, which could integrate sort of with our product to ensure that it's properly utilized. And maybe even, for example, if a user creates a package, a basket of products, so to speak, we actually integrate with those health apps and automatically update the daily calorie intake, which would be quite helpful since it means the user doesn't have to input all the data manually, which sort of can be time consuming and actually discourages them from entering this information. So just as a summary, we present a AR and OCR system for comprehending nutrition labels, which detects, recognizes, and standardizes lab data under real-world suboptimal conditions, which paves the way for healthier consumer decisions in the future. So, any questions?
Thank you, Rostislav, and thank you for a very good presentation. And sorry for not introducing you correctly.
No problem.
The presentation is open for questions. I have one question, if it's okay.
Yeah, absolutely.
Does any of your applications need approval from the outside? For instance, OCR, is that something you bought commercially, or did you establish it yourself?
Good question. So Zosia is actually not commercial. It is a common library called Tesseract, which is open source. So essentially, there is no external approval process. It's just a research prototype which is based on Python. So it uses the common libraries for processing data primarily. Tesseract is open source for both research and commercial use. So if you wanted to drop a commercial OCR, like, I don't know, Google version, for example, we could do that. It's an area for future improvement. But in reality, even if we stick with neural networks, there is no real when to log in. They're all open source. The only limitation is basically just running them on our hardware. So it says the limitation is not really licensing or like when to log in, but if you can run a certain neural network on a mobile phone realistically.
Thank you. Other questions? Then I have one question. Sorry, Kiko?
Okay.
Yes, thank you for your presentation. At some point, in early slides, you mentioned a tesseract, which is an interesting geometrical object, and I wonder how you incorporated that in your system.
Yes, so that's a good question. A tesseract is actually not a geometric object. It's not like a 4D cube. It's just a name for the open source library. It Google's open source text recognition library. I think they just pick a cool mathematical object as their name, but no such mathematics are used in the process. So the idea behind an OCR engine is a piece of software which looks at an image and tries to read the text from it.
And one question. Are there more questions? Otherwise, I have a very simple question.
Okay.
Does this system work on Cyrillic alphabet as well?
Yes, so early in the talk, I mentioned that both Ukrainian and English dictionaries were used. So the English one is sort of built into Tesseract, and then Ukrainian is a Cyrillic extension, which we have used. In our training, we have used them side by side. In practice, most of the text we trained on was actually not English at all, because it's kind of hard to combine with, like English consumer products. It was mostly Cyrillic. So it's not a blocker, it's basically supported out of the box through this language pack. And it's actually one of the reasons why we've chosen this Tesseract library.
Thank you, Rostislav, for a very good presentation. I think our next speaker, I think we are a little ahead of time, but our next speaker will be Professor Adamenko. And the title of this talk is Conceptual Model for Information Technology for Assessing the Quality of Electronic Book Publications. So, Professor Adamenko, are you ready?
I think there's another talk before that.
Yeah, isn't Natalia next?
Yeah.
The schedule?
Litchinitser, yeah, next.
Maybe I have an old program. Do you have the updated program, Kiko?
Yes, I do. So let me proceed with the introduction then here.
Thank you.
So our next speaker is Natalia Litchinitser. I hope I pronounced it correctly, from Duke University, and she's giving a talk titled "Structuring Spatiotemporal States of Polarization." And go ahead, Natalia.
Just 1 second. Can you see my slides?
Yes.
Yes.
Okay. Good afternoon. My name is Natalia Litchinitser, and I will be talking about some of our results that we just recently obtained in our group. So, well, I think it's expected then when we talk about polarization, we of course bring up a concept of Poincare sphere. So I will briefly review what we already know about it. Then I will talk about structured light. Of course, at this conference, I don't need to introduce structured light, but I will just tell you what a type of structured light we're looking at. And then I will get to our main topic of spatiotemporal structured light and tell you how we describe it using a Poincare sphere. And at the end, I will show you some very recent results which we obtained this summer on spatiotemporal optical skirmions. So, first, if we look, let me just minimize this screen. Okay. So if we look at different polarization states of light, we know that we can have all these different polarizations, horizontal, vertical, something in between, right circular and left circular. And of course, all of this can be described by Poincare sphere, which of course is named after Henry Poincare. And as we all know, we can write the electric field in this form and represent it in terms of these different polarization states. And depending where we are on the sphere, we basically go through all those polarization states which I showed you on the first slide. So, well, and of course, this has been discovered a long time ago or suggested as a way to describe polarization. So, well, of course, since then, there were many developments. And so how we characterize polarization states, especially in experiment, we usually look at Stokes parameters. So I just put them here so we all remember them. And then of course, we want to go beyond simple polarization states and look at something maybe more involved. Why? Because, well, in different fields, we use different structured light beams. So we specifically were looking at applications like imaging, communication, and things like that. And there, for example, in communication field, people already used all different degrees of freedom, like space, wavelength division multiplexing, time division multiplexing, polarization multiplexing, but not really, for example, OEM degree of freedom, or more generally spatial degree of freedom. Well, it's not that like people didn't look at it. Of course, there are many groups working on it currently, but I'm talking about commercial implementations. This is still this degree of freedom is still in the context of active research. So there was this really nice review paper a few years ago by Andrew Forbes and his co-authors, where they tried to summarize what all different groups are working on. And of course, I won't be talking about all these different structured light states, but just interesting to show how many of them, and there are others which are not on this plot. For example, optical nodes are not here. But again, this is just to summarize what all different groups are working on. So, well, let's start with looking at what people have used in the beginning. So that was amplitude, and topology, more recently, orbital angular momentum, or phase, more generally, or topological charge, we can also call it. And so in this context, instead of just right and left circular polarized beams and all different variations of linear polarization, we can look at, instead of just Gaussian beam, at all these different types of beams, like Hermite-Gaussian, Gaussian beams, and all these interesting beams like Innes-Gaussian and Matthew beams. And of course, we've seen already many very interesting talks on some of them at this conference. And well, we're mostly interested in this talk in Vlokh beams. And see, so well, just to remind you, well, we can write Gaussian beams in this general form, generalizing from Gaussian beams, and well, they look like donuts or donuts with multiple rings. And if we plot the phase, we obviously have singularity or multiple singularities. And this is, of course, was described in 1990s and by Les Allen and co-authors, and Marat Soskin and co-authors. And so of course, the main parameters here are radial index, waist radius of the beam, Vlokh polynomials themselves, and azimuthal index. So, well, those beams have been studied for a while, and we can, of course, also represent them on the Poincare sphere. So let's see how we can go from basic Poincare sphere, which we just recently looked at, to kind of higher order Poincare sphere. That was the idea proposed by Giovanni Meloni and Bob Alfano in 2011. So they showed that we can take Gaussian beams as a basis. So we basically stick them here. So we modify the expression for the basic Poincare sphere by using LG minus L and LGL beams here. And then we can present those states at kind of their own higher order Poincare spheres, shown as examples here from L equals to -1 and +1. So again, you can see that depending where we are on the pole, on the equator, we have all different complex spatial vector beams. Okay, so that's still something we already all know. So we're back to this complicated, well, this many degrees of freedom in terms of the beams we can use. So now let's look at frequency. So frequency has not been considered in terms of those Poincare sphere representation, because we basically assumed its frequency is fixed. Again, starting from the basic Poincare sphere, we can modify it, and following this very nice paper by Vlokh and co-authors, published just about a year ago, we can now also take into account the spatial and spectral dependence of the beams. So by using this combination, so basically what we're doing, we're making the expression a little bit more and more complex. We already have like a Gaussian beams here. Now we add Hermit-Gaussian at a given frequency, and different orders of Hermit-Gaussian following this paper. And so again, we can represent those on Poincare sphere. And what this paper have shown last year that we can basically represent the spatial spectral shaping of the beam. Well, this was really interesting discovery, so we looked at this paper, and that actually inspired our research, because we asked the question how this constructs which they're putting on this Poincare sphere would look like in the time domain. And of course, this paper aimed at structuring light in the spatial spectral domain. So of course, if we plot the pulse in the time domain, we will have different polarization states at different frequencies. So, again, next step would be to look at the time domain. Can we structure those beams of light, or those actually pulses of light in space and time, not just frequency? So that's what we did. And well, before I talk about our work, I wanted to mention this emerging field of spatiotemporal optical vortices, or other types of higher order spatiotemporal modes. So they have been discovered in first in the context of actually nonlinear optics, in context of light filamentation, and then it was shown by so this was by Howard Milchberg, and then it was shown by Kevin Jean that we can also have those beams in linear optics, and as well as Howard's group. So it was very interesting to know that we can observe them not just in very high power beams such as filaments, but we can actually observe them in linear optics. Well, then Joe Carpenter and co-authors showed that we can do way more by kind of arbitrary shaping spatiotemporal beams. So that was another very nice work. And but nobody really talked about polarization in detail in those works. So that's what we wanted to address. So how those scalar spatiotemporal optical vortices look like is shown here. So it's basically, well, very much like the beams we looked at already in the spatial domain, but now you can see that in these brackets we have both pulse width dependent term or time dependent term, and also the spatial term with some given waist radius, and then the rest of it is just the envelope and the amplitude depending on both parameters. So yeah, and this is what people call STOVs, or there are a couple of other abbreviations introduced in the literature by Vlokh and other people, so different abbreviations of the spatiotemporal thing. Well, how they look like? They look like really spatiotemporal shaped beams. So if we plot them in the this coordinates x, y, and t, not z, we will see actually a donut. But now this donut is basically not only in spatial domain, but in the space and time. And so if we plot the cross sections, we will see, say, for the L equals to 1 or L equals to -1 topological charge, we will have our like phase singularity, which we have seen before and all familiar with. But now the difference is that we can see it in the x and t plane, not x, y transverse plane. So Okay, again, back to our basics. I will start with this for Poincare sphere, and now modify it further at the same way as, for example, Alfano's paper replaced basically the, oops, let me go back, modified this expression by adding Laguerre-Gaussian beams in both terms. Now we are looking at this expression and thinking, can we actually describe those spatial temporal beams using the same formalism? And indeed, when we looked into this more closely, if we place these stoves or spatial temporal optical vortices into this expression, we actually can design new Poincare sphere, which would describe those spatial temporal beams, and we call it spatial temporal higher order Poincare sphere. So how it looks like, just one example of this Poincare sphere is this for topological charge L equals 2 + 1. So you can see that we're getting beams looking more and more complicated. And what's important again, since this is kind of the main topic of my talk, all those states, if you look at them, are represented in XT domain. So it's truly a spatial temporal structured beams. So, well, if we now plot those beams in terms of, for L equals to -1, we get yet another family of the beams. So we basically, again, just like for spatial beams only, we can now create a family of Poincare spheres, each for a given topological charge. Okay, well, that was so far theory. We actually went and built the experimental setup to demonstrate some of those states. I won't go into details, but so we basically create those beams using spatial light modulator and largely following the papers on stoves that other groups published, but now we modified further to basically be able to switch to add polarization state to this. So well, this is our results, very recent results on spatial temporal vector beams. And so you can see that this is for charge +1. So on the like this nice looking perfect beams are of course theory, and less nicely looking beams are experiment, but generally they follow really well our predictions. And so same thing for L equals to -1. Again, theory and experiments, so seems to follow really well, so that kind of confirmed that indeed we can describe those states using the spatial temporal Poincare sphere of higher order. And then we thought, well, we can move, we can get even further. We can represent those look at the spatial spectral domain. And so the question was basically the previous paper by Vlokh and co-authors was doing the opposite. They were structuring beam in spectral domain, and then in the time domain it was not clear what would happen. Here in our case we aimed at structuring in the time domain, so of course we had a question how those beams would look like in the spectral domain. And so we plot here what happens in the say y omega domain. So we can see that at each frequency, so this red line corresponds to different frequencies in this domain. We have different states. And of course, as this is expected, because we aimed at structuring the beam in the this xt domain. So of course, in x omega domain, we expect the spectral frequency dependence. Okay, so let me go to this. So the final result, which I wanted to share, is we went a little further and thought, well, now that we can shape beams in space and time, taking polarization into account, well, there are these very interesting objects which people in optics started working on in the last probably 20 years or so. But those are optical skyrmions. Of course, as a field started in 1961 when Tony Skirm proposed the concept of skyrmions, but not in the optical domain. Then, of course, those structures have been observed and predicted and observed in many other fields, physics areas, and probably the most well-known is magnetic skyrmions. But recently, those structures have been described in optics, and so we thought, well, maybe we can also describe and demonstrate it in optics. So we were interested in whether we can actually describe them using this unified approach of higher order Poincare sphere. And that's what we did. Again, I'm sure you have seen this simple equation enough. But again, we start with that, and now we modify it further. So now we do something a little bit more complicated. So we stick a Gaussian beam into one kind of part of this equation, and the stove in the other part, and then we can plot for different theta and phi in this spherical domain, different states corresponding to, well, topological charge +1 in first two cases and -1 in the third case, and different parameters corresponding to theta and phi. And indeed, we can create this way by moving around the Poincare sphere. We can create, for example, what's called new type of skyrmion, a Vlokh type of skyrmion, or anti-skyrmion type. So, well, let's see if we, oops, yeah. Well, further we can create, like if we change those parameters, again, we walk, all we do, we walk around on this Poincare sphere. So depending on those angles, theta and phi, or topological charges. So here you may notice we change to topological charge 2 or -2. So we can see another type of like second order new Vlokh and anti-skyrmion. So again, the whole family of new states that can be described exactly the same as previously. Simple polarization states have been described, stoves have been described, and so on. And finally, we performed experiment. It wasn't easy because things are getting more and more kind of involved in experiment with getting those more complicated states. But eventually we were able to get some, well, not perfect, but something closely resembling what we get in theory for some examples of skyrmions. So again, those are polarization textures in X and T domain. And finally, I want to summarize my presentation by saying that we proposed a spatiotemporal higher order Poincare sphere to describe different spatiotemporal states of light. And we applied it to stoves, and later we applied it to skyrmions. So we described spatiotemporal optical skyrmions. Again, the important thing is they are not just spatial skyrmions studied in the past, but we, again, now we're doing everything in space and time domain. And so, of course, I'd like to thank the funding agencies that supported this work, and my group members who are all responsible for this work. And thank you very much for your attention.
Thank you very much. Very interesting talk. Are there any questions? Okay, I have a question. Fascinating beams now that you vary frequency and time. Now, for those measurements on time, do you do some kind of a gated type of measurement to get time slices of the beam?
Yeah, so basically if we go to, oops, where is experimental step? Let's see. Okay, somehow my PowerPoint is really slow. But yeah, but essentially, yeah, we basically have a delay line, and we kind of slice one pulse against another, and this way we get different cross sections in time. Oh, maybe it's actually got back to me. Let me see if I can get to the experimental setup. Oh, okay. Yeah, so basically here we have a kind of so we send the beam, split it, and then this is the pulse shape or beam shaping part. So we have a spatial light modulator, and so we use a gradient to spread all frequencies. So we shape them, and then at the camera we combine it with another beam which went through the delay line, and this is how we basically slice one against with like a not shaped beam with the shaped one.
So is it a pulse laser that you use?
Pardon?
It is. Do you use a pulse laser?
Mm-hmm.
Okay. Thank you. Are there any other questions?
Maybe I can ask a question. Thank you, Natalia, for the very nice presentation. So in your stoves, the polarizations are on transverse planes, but the profile is on a longitudinal plane, right?
So basically, the topological charge or singularity is in, say, xt or yt plane. Yeah.
Mm-hmm. So yeah, xt or yeah, that's the distribution, the
Yeah.
distribution, but the polarization is transverse because it's fairly bright.
Mm-hmm.
Okay, thank you.
We still have time for questions, or more questions. Okay, Steen has a question.
It's not to be facetious, but where do you see the first application of skyrmions? Is that in physics, general physics, or could you foresee some place where it'll be applied?
Of course, definitely in studies of how light shaped in this form interacts with different media. So this is more on basic side. I've seen, honestly, I'm not sure yet if how realistic it is, but I've seen ideas on using skyrmions for high resolution imaging. And indeed, if we look at the textures, not this skyrmions because these are free space, but we have another work where we have a really near field type of skyrmion on the very small scale. There we get the texture changing on the scale of like wavelengths over divided over 60 or something. So it's deep sub-wavelength scale. So if we could figure out how to use it for imaging, that would be really nice because it basically samples in this really nanometer scale.
That sounds interesting, definitely. Thank you for a very good answer.
Okay, see no more questions, but we are a little bit ahead of time. I don't know what the organizers do, if they want to proceed with the next talk or. Thank you very much, Natalia. That was pretty awesome.
I think the next talk has been cancelled.
No, maybe Professor Adamenko here is present here.
Yes.
Yes, okay. It's without changes. Okay, thank you.
So it's okay to proceed. Is that right? Okay, Professor Adamenko.
You can see my presentation.
Yes, we can see it. Thank you.
Thanks. The topic of my report is the optical vortices generated at multi-stage optical system with less optical elements stressed by bending. The relevance of this topic lies in is following. Using composite vortex beam increase the data transfer rate. Therefore, in the last few years, considerable attention has been devoted to searching for opportunities to generate composite vortex beam, their modulation and demodulation, and also multiplexing and demultiplexing. Today, on to of main methods of generating optical vortices is the use of the so-called Q plate. She is a linear fast plate retarder with a phase delay of pi, where its main axis of the retarder repeats Q time, the azimuthal angle. These Q plates generate an optical vortices with a charge that is twice of value of Q. To date, various combinations of Q plates, for which the values of Q are equal to 1 second and 1, with half-wave plates have been investigated. These combinations are equivalent to a certain individual Q plate. As a result, it has been theoretically shown that for this optical system using n Q plates with different values of Q, the number of different combinations of this value is equal of 3 times the value of n. Therefore, the use of multiple devices for generating optical vortices in an optical system under certain conditions can lead to a significant expansion of the spectrum of charge of the generated vortices. On the other hand, a similar effect can be assumed using torsion stress crystalline element, which differ from Q plates in a linear radial distribution of the phase difference, which can be operated by applied torque moment. We have theoretically verified the possibility of expanding the spectrum of vortex charge generated using multi-cascade optical system based on the lithium niobate crystal twisted around their optical axis. As a result, analytical expressions for the electric field parameter of the output optical wave were obtained for a four-main type of elementary cascade that allow the generation of vortices with charge +1 and -1, and also provide the matching of adjacent cascade in the multi-cascade optical system. At the same time, it was shown that when using the appropriate number of sequentially located cascades, each of which belongs to a certain type from the above, it is possible to generate a vortex beam with arbitrary integer vortex changes, including 0. The application of the mechanical torsion stress to the optical element requires fairly complex equipment, which significantly reduces the scope of practical use of torsion stress element. In turn, optical elements stressed by bending are devoid of this disadvantage. In addition, they can use glass, not just crystals. The above explain the importance of the research of the property of the multi-cascade optical system with bending stress glass element. To describe the properties of the bending stress glass element, we write the equation of the optical indicators of stressed medium in rectangular coordinates that establishes a relationship between the components of the tensor of optical dielectric impermeability of the piezo-optical tensor and of the mechanical stress tensor. Then we look for a solution of this a caution for the case of a medium stress by bending, which in stressed state is optically isotropic, for a cross-section with a plane which is perpendicular to the direction of the light propagation toward the bending stress glass element. To do this, we will find the eigenvalues of the corresponding tensor. As a result, we obtain the ratio for the barrier regions of the bending stress glass element. In this ratio, the optical stress coefficient, which characterizes the relationship between the barrier regions and the external stress that cause it, is the tabular quantity for optical glasses. The bending stress glass element, like the torsion stressed lithium niobate crystalline element, can be described by a Jones matrix of the arbitrary phase retarder with certain thickness toward which a light beam of certain radius passes. Considering the Jones matrices of these elements, we can obtain the condition under which the bending stress glass element in an analog of the torsion stress lithium niobate crystalline element, and all the provisions obtained regarding the torsion stress lithium niobate crystalline element are valid for it. Let's call it the compliance condition. Thus, using the bending stress glass element for type of elementary cascade can be created, which allow generating optical vortices with charges +1 and -1, and also ensure the coordination of adjacent cascades in the multi-cascade optical system. As a result, it is possible to generate a vortex beam with arbitrary integer vortex charges, including 0. Let's consider the possibility of fulfilling the compliance condition from different types of light application to the bending stress glass element. Strictly speaking, we find the radius of the light beam between which the compliance condition is fulfilled with a certain given accuracy. As can be seen, the fulfillment of the compliance condition is in principle possible when the expression of shear stress and normal stress can be written respectively as the products of the sine and cosine of the azimuthal angle by a certain radial function. Thus, in the case of the line concentrate loading, given the structure of these expressions, the fulfillment of the compliance condition is impossible over the entire range of the bending stress glass element length. In turn, in the case of the full distributed loading, given the structure of these expansions, we can write the relations for the maximum absolute deviation from the complex condition as the function of the relative length of the bending stress glass element tau, and the relative radius of the light beam passing toward it rho, for the entire range of the bending stress glass element length. In the case of the partial distributed loading, similar relationships can be written for the entire range of the length of the light distribution, given that the diameter of the light beam is tangential of this length. Therefore, in case of full distribution and partial distribution loading using the appropriate graphical dependencies for a certain selected value of the maximum absolute deviation and for a certain given thickness of the bending stress glass element, the length of the bending stress glass element and the light beam diameter can be determined, which when the absolute deviation from the compliance condition does not exceed to the selected maximum value. To experimentally verify the results of our theoretical analysis, we used an image polarimeter, which was previously applied to study the parameters of the optical anisotropy of the torsion stress lithium niobate crystalline elements. This image polarimeter consists of light source section, polarization generator, sample section, polarization analyzer, and controlling unit. In this case, the sample section represents a Loading module, which is shown in the photo. The partial distributed Loading was chosen given the greater convenience of its practical implementation and better operating characteristics compared to the full distributed Loading. For experimental research, we use samples of optical glass F1, which has one of the best optical stress coefficient. As can be seen, the experimental distribution of optical anisotropy parameter in F1 optical glass sample, optical indicates rotation and optical phase difference, induced by partial distributed load 0 and 286 Newton, indicate the occurrence of the topological defect in this sample. The black circle of this distribution indicates the region of the approximate fulfilling of the compliance condition. Thank you for your attention.
Thank you very much for your talk. Are there any questions? I have a question. Previously, Tom Brown at University of Rochester really got us started with these vector Poincaré beams. He also had a stressed optical element. That's how he constructed Poincaré beams. And so do you see any polarization type beams in
the input polarization is circular polarization.
Okay, so it's all uniform circular.
Yes. Output polarization we investigate of a linear polarization. It's scanning the output beam.
Yeah. I was thinking that since in that other system they were able to produce a vector beam from the stress. I was wondering whether you could do the same thing and then create some kind of vector type.
We investigate multi-cascade. This stage is the research on the one module, Loading module. This module, the two identical module is this stage of the investigator. We research the with compliance theoretical analysis and experimental data. The research відповідно
According to. According to. Відповідно, according.
Так. But our research don't finish it. It's відповідно in future we use two module and investigate the multi-cascade. It consists two module of Loading. T stage is only one model of learning.
Maybe I can make a comment based on your question, Kiko. So that window that Tom Brown proposed, the inhomogeneous birefringent distribution naturally arises in the vicinity of an equilibrium point, the point where all the birefringence cancels. So my guess is that we see that, and this slide, I don't know if I'm interpreting the colors correctly, but it looks like in the bottom left, there's that circular pattern selected that corresponds to that hole. That probably is a naturally occurring equilibrium point where we have all the directions of the polarization. Is that correct?
Yes. We want to increase the power of loading. On T stage, we use loading weight 10.5 kilogram. In future, we need to increase the load, and the distribution of optical indicator rotation and optical phase difference will be better to compliance to condition.
Okay, thank you.
I must add that Miguel was a co-author in that work as well, the one that I mentioned.
Not a problem.
Any other question? So the next.
Thank you very much. Yes,
Yeah.
Thank you.
Thank you. It was our last report during this session. Now we start, but not now. At 4 p.m. we start the poster session, and we will meet tomorrow at 10 o'clock Kiev time during our last conference day, and it will be connected with the biomedical investigations, and where there were presented some discussions and reports in biomedicine. Thus, thank you very much, and we will meet tomorrow at 10 o'clock. Thank you.